Thank you very much. Hello folks, I'm Omer. I'm an embedded systems engineer at Erlang Solutions. I'm part of the Erlang Embedded project, which is a collaboration between University of Kent in England and Erlang Solutions, also in England. We're looking at ways of adopting, help speed the adoption of Erlang in embedded systems. And we've been playing with low-level interfaces and stuff, which I'll be talking about today. So the idea behind, let's start with the outline. We're going to look at the current state of the embedded systems, and then we'll look at Erlang. We'll skip this really quickly because you all know Erlang. And I'll focus particularly on the actor model and talk a bit about why we think it makes Erlang a great fit for the embedded systems domain. And then we'll talk a bit about how we model and develop Erlang systems, embedded Erlang systems, a bit about the project, and some fun stuff that we've been playing with. Unfortunately, the term embedded systems is a bit like the term cloud these days. It can mean pretty much anything and everything. But traditional definition of embedded systems is a particular system that's designed to do very specific functions and features that are very limited. So going by that definition, you could say that an old mobile phone was an embedded system because it could only make calls and send SMSs, etc. But if you look at a modern modern mobile phone, it's more like a general purpose computer. You can play Angry Birds and check emails on it and stuff like that. So that kind of goes against the definition of the term embedded systems. But I think it's a better idea to just think of embedded systems as small devices that run processors that are not, say, x86 or desktop or server class processors. I'm talking about ARM or MIPS-based devices, basically. So embedded systems are getting more and more complicated, and we're utilizing these system-on-chips platforms that are becoming larger, more complicated, and very difficult to manage with the current tool chains and methodologies that we have in the embedded domain. And we also have this beautiful term called the Internet of Things, which practically means everything is becoming connected and distributed. There's some fun examples of that I'll talk about in a minute. And then we're seeing more and more multi-core devices that really is not fun to program using the standard tool chains that we have in embedded world. And we also see lots of co-processors being bolted onto our little CPU cores to do specific processing tasks. It's an exciting time to be a hardware engineer or an embedded designer because we have some very interesting stuff happening, like the rapid prototyping, 3D printers, and putting stuff on Kickstarter and getting community funding for it, etc. So really, all these combined make designing contemporary embedded systems or the future embedded devices really difficult. Let's look at the Internet of Things. Unfortunately, you can't really see anything with this, but this is just to show you the scale of distribution of embedded systems in our world. So we have buildings, IT, network, retail, transportation, industrial. It's everywhere. There are predictions that we will have 50 billion devices in a couple of years' time. More devices than there are humans around. And if you look around, you'll see people with tablets, mobile phones, 3G-enabled Kindles, and there are just too many of these devices. And managing the distribution of these and the context that they act in, etc., it's becoming really difficult. And some would say that it's actually getting a bit ridiculous as well. So we have fridges that can tweet, or you can upload your pictures to your fridge, apparently. Who would want to do that? I have no idea. Or we have distributed bovine networks where you implement sensors to cow and cattle and all sorts of animals. So the applications are not just based around our homes or server rooms, they're everywhere. They're inside living creatures as well, which is quite scary. And there are also enabling factors that make developing embedded systems quite easy. The first one is the Raspberry Pi. It's a small little embedded Linux board that is extremely accessible, very, very affordable. And the greatest thing perhaps is the buzz around it and the number of exciting projects that's coming out and enabling other people to get ideas and merge them with their own ideas and create awesome things. Up until a couple of years ago, getting started with embedded Linux development has been extremely painful and very, very expensive. Now you can just buy one of these boards for not very much money at all, and then if it breaks, you don't feel bad. So my computer just exploded, sorry. And if you want to develop a custom product now, you can just buy a 3D printer and then design your own enclosure or mechanical pieces, or glasses in this case. And building a product is not, it does not require a room full of engineers, each responsible for something. Just using your desktop manufacturing capabilities, you can take an idea from the very idea phase to an actual execution of a prototype device very, very easily. Going back to the complexity of the devices that we deal with, this is what a general purpose system on chip device looks like in terms of functionality. There are loads and loads of things happening. There are different cores of processors, so you have CPU cores, GPU cores, DSPs, ISPs, I2C interfaces everywhere, and all these different devices connected, etc. If you consider that the main tool or the main language that we use in embedded world today is C, you can see how managing all these things concurrently or juggling interrupts, etc., can be quite painful. This is just another example, just to show that all these devices have this complexity built into them. We need a new way of thinking about how we architect these systems. To back that claim up about C, this is a recent graph that I pulled from a website that shows that the prevalent or the dominant language in embedded systems last year was C. And funny enough, the trend line is increasing. So we're going to perhaps get more and more C. And there's nothing inherently wrong with C. It's just not the right tool to deal with the modern problems that we have, like concurrency or distribution. These things are better handled with higher level frameworks or higher level tools. And that's what I'm going to talk about in a minute when I get to the Erlang bit. So how we actually architect these embedded devices, what are the methodologies that we use? So 3 approaches. You can either do bare metal programming. It means that there is no operating system. You just write really low-level code, write your own handcrafted interrupt service routines, etc. This is not very realistic for a moderate complexity device, because you need to write a lot of very fine-tuned, very low-level code, and generally this is only viable if you are producing something extremely specific or niche, and you need the speed. By ditching the operating system, you get extra speed, obviously. The second common one, I think, is the RTOS, the real-time operating systems. This is a very minimal operating system that gives you certain primitives that you can build applications with. And there are some parallels between RTOS world and Erlang, which I'll mention in a minute. The third one, and I think the most popular one today, is the embedded Linux, which is essentially Linux but smaller and with some interfaces, external interfaces that will let you talk to hardware, etc. For the project, we're only interested in the RTOS and embedded Linux class devices because we can't run Erlang on bare metal yet. So in an RTOS, you get the notion of tasks akin to our Erlang processes. And then the operating system itself gives you primitives or the facilities to do some messaging between these tasks. It uses shared memory. Hardware can be quite dangerous if it's not managed properly. So you also get mutexes, semaphores, locks, facilities that will let you do safe control of hardware. And the operating system also provides some scheduling as well. If we look at embedded Linux, it's again, Linux, but smaller. But when you go from an RTOS to an embedded Linux, there are certain mismatches in the methodologies that you are used to. And also accessing device drivers, etc., or accessing devices via device drivers, it's quite messy. So we are trying to look at ways people architect embedded systems using RTOS as embedded Linux, and then offload the features or the bits that make more sense in higher level languages to Erlang, while still keeping the lowest level interfaces in C or any other language that you might want to use. So just to repeat myself, we are not trying to replace C, we're just trying to make things much easier by using Erlang to deal with the higher level complexities of the system. So we all know Erlang is a declarative, functional, concurrent. I'm not going to read this all. There are some very relevant features that make Erlang a great tool for embedded systems. It feels kind of weird when I have Joe and Robert in the audience to talk about Erlang, so I'm going to skip these slides quite quickly. So one interesting thing about Erlang is that I think it's fair to say that it was originally designed for embedded systems. Telephony switches are, by the definition of the term embedded systems, embedded systems. So they were managing calls using external links, and because of this legacy, Erlang has great facilities to talk to external bits of code or external hardware via external drivers, etc. It's one thing that's crucial in embedded systems is that you need to be able to recover from error conditions or failures. And Erlang, again, does provide great tools to create robust systems. And it also implements the actor model, which lends itself very well to abstracting silicon. So silicon, by its nature, runs in parallel. So each individual function that you have on your system-on-chip device is independent from the rest of the system. You do have to, from time to time, communicate between those blocks, essentially. But really, you can architect or model your system-on-chip system using a set of Erlang processes, actors, really nicely. We talked about this just a second ago, but fault tolerance and being able to recover from a failure condition is absolutely crucial in embedded systems. And again, because of the history of having to control external devices, Erlang has great facilities to deal with this problem in which you can have NIFs or you can have ports. And this is crucial when you're trying to control external hardware. So I'm trying to approach this from a bottom-up sort of level with this project, because I think that if we can have a fine grain and structured control of the actual hardware itself, then creating applications on top of a well-managed system will become much easier. So when I say we have to talk to hardware, I mean we have to create sensible driver mechanisms that will let us control all the little bits and pieces of functionality that we have in our system-on-chip devices. So the actors are great because, as I've mentioned, you can think of your little system-on-chip device as having independent little blocks that run in parallel. And actors make modeling this system quite easy because they're self-contained and there's no shared state. And using actors, you can build very modular systems that you can slot into your applications, etc. So we all know about these. It's they use asynchronous message passing. This is, again, an important feature that can be used in architecting embedded systems because most peripherals do communicate using some form of a serial bus or just a bit-banged interface, etc. And the ability to queue messages in the inbox and then deal with it and do some checks on it, etc., is a very useful tool. And the fact that actors only have limited capabilities, perhaps, it works in our advantage as well. So they can either make local decisions, change their internal state, spawn new actors to deal with things, or send messages to other stuff. And using these primitives, we can model individual functionality within our blocks quite nicely. And let it fail is, again, something that's very relevant because hardware fails, and being able to recover from it is absolutely crucial. Again, I'm going to skip these slides because we all know about these. But being able to contain errors as they happen in our runtime system is good, very, very good. Because let's say your button driver failed. You don't want your entire embedded system to fail just because a small portion of your system has failed. So by using the trap exit flag, we can make sure that the propagation of errors are contained within individual modules and do not affect the other parts of the system. So again, let's have a look at this. You can see that some of the things are actually connected together. And you can use a collection of actors to create subsystems and then use maybe a brain process to tie everything together. This almost is replicating the black box methodology or even the hardware description languages that the hardware guys are used to. Being able to just implement small modules and have a top-level description of your system with signals connecting things together is a very hardware. It's very similar to the methodologies that the hardware guys use in, say, the FPGA world and logic design world and so on. Now, this sort of fine-grained abstraction does have its advantages, and sometimes it's also a curse. You can create shorter modules, and depending on how you structure your system, you can maybe reuse the little blocks that you have done. And application code tends to become simpler because you don't have huge amounts of error checking, etc., embedded into modules. And testing is an interesting feature because traditionally embedded systems require a lot of testing, and they have to go through quite a lot of certification stuff if they're going to be ever used in, say, military or medical sectors and so on. So this is a double-edged sword. You can actually do some quite cool things just using very, very fine-grained Erlang actors, or it may just become too difficult, especially if you're working as a team. And the actor model itself has no inheritance or general hierarchy, but luckily OTP does give us the sort of primitives to structure things sensibly. And for certain embedded applications, the async message passing can be a bit of a problem. But for 95% of the stuff, it's OK. So with all things considered, we think Erlang is a great orchestrator of systems. So using Erlang as a systems language does make sense. And that's why we're trying to develop libraries and tools to control hardware and to demonstrate that we can afford to run a higher level tool to manage the complexities of the embedded systems. OK, let's talk about hardware a little bit. On a traditional embedded Linux system, you have two methods of accessing hardware. You cannot, because these peripherals are generally, actually most of the time, memory mapped, you can just open dev mem. But this is I mean, I'm sure you've done it before in your first computers when you're learning how to program, etc., writing directly to the screen maybe, etc. But the problem is this is potentially very dangerous. If you do some dodgy pointer arithmetic, you may actually destroy your system by twiddling some bits in a power management unit or something along the lines of that. So the other safer and more sane method of doing this is via using kernel modules. And generally, the kernel modules for embedded protocols or hardware tend to expose sysfs entries that you can interact with just like normal files. But if you were to just say, I'll write everything in Erlang, you don't have to dive into C and pointers and that sort of stuff. As an example, I'll show you a little GPIO driver that we have. A GPIO is a general purpose I/O device, which is essentially a pin that can be an input or an output. So before we can use a pin, we have to initialize it via pin and direction variables. And the way we do it is very simple. We just open sys class GPIO export, make sure that all the entries are created. And then we just write the direction of the pin that we want to use it as. There are two options. It's either in or out. And then we have a file descriptor that we use to talk to the pin afterwards. If you have a Raspberry Pi or a BeagleBone, if you actually run this, you'll be able to control LEDs and stuff. And writing to it is just a simple case of rewinding the file and sending 1 or 0 to it. And reading it is exactly the same. It's just the other direction, of course. And you can also release the pin after you're done with it. So this is essentially what your GPIO driver can look like. This doesn't work, unfortunately, for all the cases. There are some odd cases where you have to use poll system calls or select and that sort of stuff. And then you'll have to either use ports or C ports maybe to prevent your runtime hanging if you were to use an if. But generally, for simple stuff, you don't even need to go down to C level to write your drivers. So GPIO, concurrent GPIO access. Let's say we have a pin process that talks to our actual physical pin 17. We can just use a little structure where we send messages directly to it. But the problem is, because we may have other processes sending conflicting things to the pin, this may cause problems. You don't want to rapidly write to a pin conflicting values. If it's a mechanical, say, DC motor or something, you may actually kill it. So having a proxy process or like a little abstraction is what we're looking at. So this is a very simple example, of course, but we can have a GPIO proxy that can prevent clashing pin states. And we can also implement all sorts of different things to it, like detecting the toggling rate, if it's dangerous, slowing it down, or generating an error condition. We can do sequence detection, and so on, utilizing the inbox that we have thanks to the actor model. Arguably, this is just a lock in the traditional sense of embedded design, but not quite, because you can do some pretty clever stuff with it as well. Now, we have a little demo. I don't know how well you can see it, because I should have inverted the video, really. But just to show you that this works and it's kind of fun, I'm going to have 3 LEDs connected to 3 different pins. And this is just a simple module that I have. I'm initializing it. The first one is connected to 18. So if you can't read it, it says L0 equals LED start 18, 21, and 22. Here you can see the actual light emitting diodes. I turned one on, and then I made a syntax error. I turned the third one on, and I'm just going to have the middle one blinking every half second. While it's doing that, I can turn that one off, and then turn it on again, and so on. Now, this is obviously a very simple demo, but the idea of being able to control hardware separately, or hardware blocks separately, is applicable to higher level complexities in systems that we have as well. Another thing we're interested in is being able to move our applications across different platforms easily. So if you think of a hardware driver and the little application code that uses it, you can divide it into 3 different bits. The first one is the component API, which is a high-level set of functions that your, say, little sensor might use. The second one is the peripheral API that actually lets you talk to the hardware, depending on which interface it uses. And the third one is the actual driver implementation itself. Now, the component API and the peripheral API are actually universal. They don't change. I mean, I2C bus is I2C bus, depending on which platform, or independent of which platform you use. And likewise, your sensor will only have, you know, a predefined set of functions on every platform. So by keeping the 2 layers, the 2 higher levels universal, we can move applications between different platforms easily. So an example to this will be, could be a temperature sensor. So the sensor API is going to be get temperature, calibrate, maybe, something along the lines of that, which talks to the I2C bus driver that implements transactions and that sort of stuff. And then the lower layer can be sysfs entries or IO control, sys control, or it could just be memory mapped voodoo. So this is the sort of stuff that we are playing with, just an overview of the Erlang embedded project. We're also doing some hardware development to help people explore things. So this little guy is an adapter for Arduino shields for the Raspberry Pi. It lets you plug one of the many hundreds of expansion boards that the Arduino platform has to the Raspberry Pi to provide further functionality to your Pi. And this one is, some of you might have seen this. We used this in our Raspberry Pi tutorial 2 days ago. It's a little demo board that pretty much breaks out all the embedded protocols that the Raspberry Pi GPIO expansion header has. So we have a port expander here that has some LEDs and some extra switches. We have an SPI analog to digital converter here, a temperature sensor and a little potentiometer and some buttons and so on. These are all open source stuff, by the way. I really need to update the Erlang embedded site, but they will be available there very, very soon. The idea behind this is eventually we will be providing some modules or documentation that you can download and follow along to look at how you can control things concurrently using Erlang. Of course, you don't have to build one of these boards. We also provide a simulator, again, which will be released soon, hopefully. So if you don't have a physical hardware platform, you can use simulated hardware modules and, again, experiment with concurrent hardware access. We're also looking at how we can expand this to expand the project to look at interesting new and novel architectures that we have, like this Parallella device, which utilizes an Epiphany processor that is a very low power 16-core device, each core being a 1 gigahertz RISC core, and see if we can offload certain things to the coprocessor to speed things up, especially in the areas of, say, image processing or voice recognition and so on. If you're interested in playing with this in your Raspberry Pi, you can download Erlang. You don't have to compile it yourself. We take care of it for you. Just go to the Erlang Solutions packages page or downloads page. And we're also putting together an extended version of our tutorial session to look at embedded Linux and drivers. You probably don't need Erlang 101. But if you're interested in learning more about how to develop embedded systems using Erlang, do get in touch. So I think that's about it, actually. If you have any questions or if you have any bits and pieces that you're not satisfied with, please let me know and I'll try to rectify that. Hey.
So I think the reason that C is trending upward in that chart is 8-bit processors, and Erlang doesn't really fit on those.
Erlang does not fit onto 8-bit processors, unfortunately, no.
And then you're running on these kind of big, what amounts to workstation level processors.
Mm-hmm.
In between, there's kind of like Cortex M4 levels of chips. Some of them have as much as a half megabyte of SRAM on the chip.
Yep.
And do you think of being able to run on something like that, which would mean a stripped down VM, I think?
We don't have any immediate plans to look at minimizing Erlang to run on, say, Cortex M3 or M4 probably class devices. But that doesn't mean you can't really use Erlang in that context. As long as you can make sure your backend services, etc., can accept, incoming stuff.
I figure that maybe you can tell me if it's accurate, that you wanted around 32 megabytes of RAM in order to use Beam.
You can run it in much lower memory than that. Probably 16 megabytes will be plenty enough.
Okay, but yeah, I'm looking at like a half megabyte.
Yeah, I don't think that's enough, unfortunately. Beam has lots of POSIX dependencies, and generally you don't get POSIX compliancy with 8-bit systems, or small 32-bit systems as well.
Do you know? Oh, sorry.
But you could make it. I mean, you could make an Erlang that ran on. I mean, Erlang ran on less than a megabyte back in the 90s. It was optimized using 32-bit machines to make it go faster. We haven't optimized it. It would be a completely different VM, but the language would be the same. You'd have different opcodes and things.
I mean, this is a 32-bit processor.
Yeah, but I mean, the original Erlang was a byte, literal bytecode interpreter that ran pretty small. Robert was a system that ran in our kilobytes.
So I think
Yeah, you need to
yes, you can do it, but you need to do a new implementation.
yeah, there has to be a new implementation. I don't see the current Beam being slimmed down to fit onto those small systems.
Would you need to redo the compiler too, or
No, you could use most of the existing compilers. Just redo the backend machine structures for all that time.
take a bit of time.
It's not good.
It's only doable.
It's
Definitely doable. It'll be quite fun to do it.
Take time.
so Robert and Joe seem to be interested. Maybe we'll see it happening.
Well, no, it's up to us to buy one of these. I mean, if he's financing, the only problem is financing it, actually.
Yeah.
I mean, doing it's not a problem, that's easy, but financing it.
Remind me to give you more Raspberry Pis and stuff as we.
Yeah, do it, we'll pay you in Raspberry Pi.
Yeah, of course, yeah. Bribe you with some Raspberry Pis. Yeah, why not?
That is the hardest part.
I wonder if Erlang on Zen is relevant to this in the sense that it kind of bypasses the.
Erlang on Zen does give us some ideas as to how to get rid of the actual userland sort of implementation stuff. And there are some other interesting things that's happening as well, like a chap has ported Erlang to run on a real-time operating system called RTEMS. That's probably more relevant to the sort of bare metal kind of stuff that, or running it on a smaller scale processor. I haven't seen any figures on that, but I'm fairly sure you can run it on much lower memory than, say, 16 megabytes, and in quite small flash as well. So there are some interesting things happening in that domain. There are a couple of people trying to run Erlang on, what's that operating system kit? So not Linux or BSD, but just a sort of very minimal operating system implementation. I can dig out some links if you want after. Ping me and I'll dig some links for you. Cool?
Any other questions? No, like I said, the Zen
So yeah, Robert mentioned that the Erlang on Zen project actually uses Beam, but instead of, you know, I think if I remember correctly, they integrated it into the kernel to an extent.
They wanted fast startup, right?
Yeah.
That was their root.
So to
Don't be fast, not small, not necessarily small.
yeah. Okay. Thank you very much.
So,
Sorry.